So I like to think of the habitable zone more as a hunting zone. So if we could travel at the speed of light, you're talking 4.5 years each way. And as it passes in front of the starlight drops. Or are we alone because everyone hates us? I mean, it's just very hard to know.
Hi, I'm Greg Mustreader, and this is my podcast on rationality, transhumanism, and trends of development in society. Today, here with me is Elizabeth Tasker, a British astrophysicist, a science writer, and associate professor at the Japan Aerospace Exploration Agency. Hi, Elizabeth.
Hi, Greg.
Thank you so much for joining in. I know you're a really notable astrophysicist. I've watched some of your talks and have read your book. This all sounds really exciting. And I have to apologize in advance for asking a lot of dumb questions because I love space, but I don't know enough about it, unfortunately. So
I was always told there are no dumb questions.
Well, for those of the viewers and listeners who also do not know much about what you do exactly, what you specialize in space, in astrophysics, can you please explain more about it, about exoplanets and all this stuff?
So my main focus is exoplanets, by which we mean planets that do not orbit our sun. So in particular, I'm interested in how different they might be from our own Earth and the other planets in our solar system, and how they form and what we might learn from them now and in the future.
Yeah, so this is a relatively new topic. As far as I know, until the end of the 20th century, there was almost nothing known about exoplanets, right?
Yes, that's correct. So it wasn't that we didn't think other stars had planets, but they're incredibly small compared to the star. So actually detecting them is really difficult. So while we suspected our solar system was far from being alone, we actually had no solid evidence until the start of the 1990s. And that was when we really started finding planets around other stars. And the first planet that we discovered around a star that was similar to our sun, actually the discovery of which won the Nobel Prize recently, was 51 Pegasi b. And one of the most fascinating things about this is that it completely broke everything we thought we knew about planet formation. And that's been a very recurrent trend really ever since. Just when we think we understand it, we promptly find a system that says, no.
What exactly we thought was right and turned out to be wrong in that case?
So what we thought, based on our own solar system, is that you have, if the sun is here, you have Mercury, Venus, Earth and Mars, and they're all relatively small, rocky planets with quite thin atmospheres. And then you have the gas giants, like Jupiter's the biggest planet in our system, and Saturn, Uranus and Neptune, and these all have colossal atmospheres. Most of their volume is taken up by their gas. And so we have this division, rocky near the sun, gas giants far from the sun. So we built up a theory that said, if you want to form a gas giant, you have to be far from the sun. And the theory was actually very sensible. The argument was that when you have a very young star, it's surrounded by a disk of dust and gas that we call the protoplanetary disk. And this is basically your building toolkit for your planets. Now, as you move farther and further from the star, you get colder, obviously. So at some point, ice starts freezing. So it goes from being a vapor close to the star to being a solid further away. And that gives you a lot more building material to build up your planets. So if you want to form a gas giant, you've got to form where there is the most material, because you've got to get really big. So therefore, you want to form where ice can join in the process and give you a lot more building material. So that explains it. Rocky, smaller planets nearer the star, and then these gas giants further away where you have this boost from ice.
Right.
But then we found 51 Pegasi b. And 51 Pegasi b is a Jupiter-sized exoplanet. But it orbits its sun-like star in just 4 days. Now, for comparison, obviously we spend 365 days going around the sun. Mercury is our nearest planet to the sun, but it still spends 88 days orbiting. So 4 days is like, what?
Very fast.
Really fast. Not only should you not be able to form a Jupiter-sized world there, honestly, we didn't really think anything could form that close. So suddenly we were like, where did we go wrong? Because I haven't really done anything terribly controversial here. I've just said, hey, it's colder further from the star, therefore you'll get ice. It doesn't seem like that should be different around any other star. So this became a big mystery. But actually, it turned out we'd actually solved it. Back in the 1980s, an idea had emerged that planets could change their orbit. And we call this migration. And it was known that this should perhaps happen. As the planet grows, it's still embedded in this protoplanetary disk of dust and gas. And there's a pull from the gas on the planet, and it typically sends it towards a star. But this came up in the 1980s, but people looked at our solar system and go, oh, no, something must stop it because we're not seeing much evidence of that. Then we had a rethink when we saw 51 Pegasi b, and we realised that certainly in some cases, maybe even most cases, migration is a serious sculptor of planetary systems. So we think 51 Pegasi b did form far from its star, where there was plenty of building material. But then, while it was still quite young, it got dragged inwards towards the star to end up on this very short orbit.
Wow, this is all... I'm sure that the person who first discovered this and it turned out to change everything he knew or she knew about that must have been a real breakthrough. But I hear that nowadays more and more exoplanets are discovered on a constant basis, and that all those new discoveries are also sometimes changing the way we have thought about the universe and exoplanets. Can you tell me more examples of such
Yeah, absolutely. So this was one of the early planets, but once the technique was established, it sort of opened the floodgates to finding now over 4,000 exoplanets. So we've got thousands of these new worlds, and we realise our solar system at least is not unique. Maybe even most stars have their own solar system going around them. But many of the planets don't fall into our standard patterns. For instance, if we go back to this idea of 4 rocky planets and 4 gas giants, you basically have 2 choices in the solar system. You're either a rocky planet like the Earth, or you're a gas giant like Saturn or Neptune. But the most common planet discovered in the exoplanet community is a planet that is larger than the Earth, but smaller than Neptune. So what is this? Is this a small gas giant, or is it a large rocky planet? And it's very hard to know that at the moment, because currently we're only really seeing these planets as shadows. So we get their size, but we don't get much about them. So if you were to ask me, what mystery would you like most to solve? I would like to know, what on earth is a super Earth? Is it a giant rocky planet, or is it a small gaseous one? How on earth does it form? Why does it not become a Neptune? Or why does it not become an Earth? What is this middle ground that we seem to be living in? And we have no analogue in our own solar system, so we can't just zip off and have a look at one. We've got to work out what they are from incredible distances.
Do you have any theory on how the answer to your question could be?
Well, naturally, as scientists, we always have theories. And naturally, as scientists, they always contradict one another thoroughly and completely. So the idea is that they may be both. Some may be giant rocky planets and some may be small gas giants. And how they form will determine which one of these they become. So, for example, for a few planets, a few hundred, but still quite a small number, we can have both a mass and a radius measurement, which is quite difficult. But if you have that, you have bulk density. And that can give you a hint about whether you're dealing with a gas giant, where because it's mainly gas should be very low density on average, or whether you're dealing with a rocky planet like the Earth, which is much higher density on average. And those suggest that you can go a bit larger than the Earth, say to about 1.5 times the size. Chances are you're still rocky. But if you go beyond that, your mass has become sufficiently large that you can't help getting a big atmosphere. And at that point, you become something that's a bit closer to a Neptune. Maybe not a full Neptune, but you've got a pretty thick cloak of gases around you, so it's not going to be an Earth-like atmosphere anymore. But to really find out the answer, we need a couple of things. Firstly, we could do with measuring more densities, because at the moment, we're only really measuring the densities of planets very close to their stars. And certainly one mission that will help with that is the European Cheops mission. And that was launched at the end of last year. And it's specifically trying to find radius for planets we know the mass of. So if we already know the mass, Cheops will try and find the radius and measure it. And that will give us more planets that we can then get an average density for. And then a little bit further down the field, we'll have things like NASA's James Webb Telescope, or WFIRST. And they will be able to do what I consider the next generation of observations. So rather than just measuring mass or size, those telescopes should be able to look at atmosphere. And if you can look at the contents of an atmosphere, you start to really get a feel for what the planet is made of.
So this telescope just has bigger lenses, or
that's a big part of it. That is a big part of it. It's a slightly different technique. So when you look at, for instance, measuring the radius of a planet, here's your star. Your planet, you're hoping, is going to go across the front of it. And as it passes in front of the starlight drops very, very slightly because the planet's physically blocking out a bit of that light. And that's called a transit, and you get a radius. Now, as that starlight tries to pass through the planet, some of it will be blocked, end of story. But some of that starlight will pass through its atmosphere. And whether it's blocked or not blocked will depend on the wavelength of light. So obviously, if you're solid, you block all wavelengths, end of story. But if you pass through the atmosphere, sometimes the molecules in the atmosphere absorb a particular wavelength, and sometimes they don't. So by measuring that transit in different wavelengths, the planet should change size very slightly. So at some wavelengths, it will look larger because the atmosphere is blocking the light. And at some wavelengths, it will look slightly smaller because the light can pass through the atmosphere. And by mapping that to the molecules in a gas, so you know what molecules absorb what wavelengths, you can get a sense for the atmosphere. But if you imagine an Earth-like planet, our atmosphere is really, really thin compared to a Jupiter or something. So it's very challenging to do it for smaller planets.
Yeah, I see. The most pressing question that most our viewers and listeners would be asking right now is, of course, whether there could be any life on such exoplanets. I've heard the term habitable zone. Can you go a little bit over that? So what's the current assumption on the probability of life, first of all, on such planets, and on where the planets that hold this probability could be located?
So I'm going to start this with a bit of a disappointing scenario and say, at the moment, we only know of one planet that definitely has life, and that's the Earth. So you can't extrapolate terribly meaningfully from one data point. It's like, where do you draw the line? Steep, flat? It could be really rare. We don't know. Now, the habitable zone sounds very exciting because you might very logically assume it is a zone in which you have a habitable planet. But it turns out there's a bit of small print there. The habitable zone is the region around a star where the Earth could maintain conditions on its surface that would be okay for liquid water. So what it really does is it says, let's take the Earth. Now, at the moment, we're temperate, we've got liquid water, hooray. If we push ourselves a bit closer to the star, the sun, what happens? Well, initially, we can cope with that because we have something called the carbon cycle on the planet, and that allows us to adjust the level of carbon dioxide in our atmosphere. So as we get warmer, we can start pulling out that carbon dioxide from the atmosphere and keep us cooler. So we end up keeping the same surface temperature. And likewise, if we move the other direction and we go further from the star, we can put more carbon dioxide back into the atmosphere and keep ourselves warm. But you can't do that forever. So the inner and outer edge of the habitable zone is the point where our carbon cycle just can no longer cope with a change in temperature, and it fails. But what that means is that if you have a planet that isn't like the Earth, so it doesn't have a carbon cycle, the habitable zone doesn't really mean anything. And I can demonstrate that very simply because Mars is inside our habitable zone. So if you put the Earth in Mars's position, we think, based on models, that our carbon cycle could cope with that and we could keep warm. But Mars doesn't have a carbon cycle. It can't keep warm, and it's a very, very cold planet. So if you have a habitable zone, you find a planet in there, it's exciting, but if it's not like the Earth, there's no guarantee it would actually be a nice temperate planet. It might still be horribly cold or horribly hot, depending on its atmosphere. So I like to think of the habitable zone more as a hunting zone. Like if there was another Earth out there that was like our planet, we will find it in the habitable zone. But just because you found a planet in the habitable zone doesn't mean it's like the Earth. So at the moment, we got to the stage where we found about 20 odd planets that are thought to be maybe rocky, and they're in the habitable zone, at least some of the time, which is pretty promising. But because we don't yet know what their atmospheres are like, we can't say whether they're Earth-like enough to maintain a nice surface condition at that distance.
So we have to hunt for some signs that the planets in those habitable zones have some Earth-like features, right?
Exactly.
How could we do that?
So the idea of this, what I talked about with the transits and the wavelengths passing through the atmosphere, if the planet transits, so if it crosses its star from our perspective, then with our new telescopes, well, at least maybe not with our quite new telescopes, but in the future that's not too distant, we might be able to measure the atmosphere content. And that would hopefully give a good indication of whether we're looking at an Earth-like atmosphere or something very different or no atmosphere at all. And that would give us more of an indication. Now, if we could see that with very good resolution, we might even pick up what we would call a biosignature. That is a signature in the atmosphere that would indicate life was on the surface. I confess we're probably not going to do that very, very soon, but we're getting close. So at the moment, we see these planets as shadows. We get maybe an average density if we're lucky. With the next telescopes that are launching really in the next few years and with better ground-based observations, we might be able to detect more of the atmospheres of these planets, especially for ones that are around what we call red dwarf stars. So a red dwarf or an M dwarf star is much, much dimmer than our sun. It's a much cooler star. And that means that its habitable zone can sit much closer to the star than our habitable zone sits around the sun. And the closer you are to the star, on the whole, the easier you are to see with this transit technique. Especially if the star is small, you get a good ratio between the star and the planet. So for these planets around red dwarfs, we might start to see some evidence of their atmospheres in the next 5 to 10 years for rocky planets around red dwarfs, fingers crossed. And then beyond that, hopefully, we'll build even bigger telescopes and we'll go after what we would call Earth analogues, which are planets that are on our orbit around sun-like stars.
How many of them could be theoretically? So how many candidates star systems do we have?
So that is actually measured. It's something called E to Earth, but off the top of my head, I cannot remember the number. So I'm afraid I'm going to completely let you down there and say, I'm not exactly sure, but I think once we start being able to see planets further from their star, the number should be significant. The question is how many of those are really Earth-like? And without finding at least another few examples, it's very hard to say meaningfully. Now, the red dwarf stars are exciting because we're going to see those first, but they have a few caveats. So in theory, they're great. They're dimmer stars, so the habitable zone is nearer the star. We can see it more easily. Sounds great. But while M dwarfs are less dim, it turns out they have a rather rambunctious past, where when they're very young stars, they tend to be very, very hot. So it might be that the planet's surface is now a perfect temperature for life, but unfortunately, during the star's younger era, it may have sterilized the surface completely and killed any life and atmosphere on it. We don't yet know if that's a big problem or whether the planet can somehow maybe avoid it. For instance, if it formed a bit further out while the star was young and dangerous. And then it did this migration in, like we saw 51 Pegasi b. Maybe it could stay far enough away during a dangerous time and then move into the habitable zone when it was a bit safer to be that close to the star. So these sort of questions will be very interesting, and hopefully we'll get some answers in the next 5 to 10 years.
Well, that's quite soon. I'm really excited right now. And what about those biosignatures? What could they look like? How exactly would we find life if it's non-intelligent, for example?
So one of the problems with biology is it's really complicated. So I feel, and part of the work I've been doing is to say, you've really got to rule out everything else. And then finally, you can say, there's no other explanation, that has to be life. So I think a big job for planetary scientists and astrophysicists over the next few years is to say, okay, we've got the Earth. We understand what's biotic and abiotic, what's biology and not biology on Earth. But supposing the Earth was a little bit different, it was a bit bigger, it was a bit smaller, it has a slightly different composition, then what would a non-biological signature look like? Because we've got to rule all those out first. If, on the other hand, we found something that was very close to the Earth, an indication might be if you see oxygen and methane in the atmosphere, because they have to be continually replenished, otherwise they form, I think, carbon dioxide. So if you see them both in the atmosphere, that suggests what we call non-equilibrium chemistry, meaning that they must be continually produced by something. And on Earth, that something is life. But it's also possible you could maybe get that through other means. For example, Titan, the moon of Saturn, has a pretty methane-rich atmosphere. And you can also get an oxygen-rich atmosphere just from water breaking up in sunlight. So you have a water molecule, it's an oxygen and a couple of hydrogen. Sunlight can split that. The hydrogen can escape because it's very light, and you're left with an oxygen atmosphere, but no biology. So it's going to be a very difficult discussion. I'm anticipating a lot of fighting for the next 10 years or so over, is that really biology, or could it still be produced by the planet without biology?
Which side are you on? Are you optimistic about finding life on exoplanets? Do you believe that within our lifetimes we will find something that tells us with high certainty that there is something there?
I'm going to be optimistic and say yes with high certainty, but I'm not sure how long it will take us to be definite. I think we will, at least I hope, we will find interesting signatures within the next 10 to 20 years. But the question will be, how certain can we be that we're looking at life? Because the chances are it won't be life that can talk back to us. I mean, that would be the absolute clincher, as if we had a conversation. But if it's not intelligent life, you've got to rely on being able to tell that signature has to have a biological origin. And it's another good reason for focusing on this habitable zone, because although life isn't necessarily restricted to Earth-like planets, our best chance of recognizing it will be if it's on a planet like our own. So if you have to pick a planet to focus on, why not try and pick one that's probably the most Earth-like?
Because otherwise it would be too complicated for us, right? To even understand other concepts of life.
I think at least at first, the planet might be so different in terms of its geology and its non-biological processes that you've almost changed too much. So therefore, it's going to be harder to say for certain that's a biological signature. And who knows what the biology would be like on such a planet. On the other hand, if it's a temperate world like ours, it has liquid water, maybe the biology will be similar to our own and it'll be easier to identify that signature.
So the exoplanet closest to us is on Proxima Centauri star system, right?
Correct. Well done. Yes, it is.
How long would it take modern spacecraft to get there?
Yeah, that's the problem. So Proxima Centauri b is the nearest possible exoplanet to us because there's no star that we know is closer. So it's our best bet if we really wanted to visit one, but the news isn't good. So Proxima Centauri b is about 4.25 light years away from us. So if we could travel at the speed of light, you're talking 4.5 years each way. And we can't travel at the speed of light. The fastest spacecraft at the moment is actually one of the Voyagers. And if that was moving in the right direction, which it isn't, it would still take about 75,000 years to reach Proxima Centauri b. Now, there are some other slightly wild projects in the pipeline. There's something called Project Starshot. And the idea there is that we couldn't really send humans anything close to the speed of light at the moment. But maybe we could send very, very tiny ultralight spacecraft there. Now, the question is whether it would literally be a flyby, like could you brake? And there's been some research and people have suggested ways in which when you reached Proxima Centauri, you could maybe slow down. But it's very speculative at the moment. And even accelerating these spacecraft to speeds, anything close to the speed of light, is still very speculative. But the idea is you could maybe do the journey in about 20-25 years was the last estimate I heard, hypothetically. So these ideas seem very crazy to me, but on the other hand, it wasn't that long ago we didn't know any exoplanets, so maybe we need a bit of craziness. But regardless of this, Proxima Centauri b is still exciting because if we can improve our direct imaging, so that is viewing the planet directly through the telescope, it's a really good candidate for that because it's so close to us, where so close is still, 75,000 year travel. And Proxima Centauri b is around one of these red dwarf stars. So all those questions I proposed about, are they really good stars to find planets around, or does their hot young past mean they neutralize the surface and kill everything? We could find some of those answers by looking at Proxima Centauri b. So I think it's a really exciting target because we would know more about red dwarf stars, more about their planets. And, hopefully we might be able to get a direct image from one of our ground-based telescopes or space-to-face telescopes, again, within the next sort of 10 years or so, if we're lucky. So that would be really exciting.
And are there already any plans to send unmanned, probably, mission to that area?
It's definitely been investigated, but I don't know whether it's got as far as a plan. Like, is it still in the research stage? I haven't heard anything more definite, but I haven't been following it super closely. Like I say, it's a bit sort of wild. So I'm a little bit more excited about the prospect of imaging directly because I think there's several telescopes that are going to try it, and I'm hoping that one of them succeeds.
Can you imagine how society will change if we were to find some proof of life on some not so far away exoplanet? How humanity would react?
I think it's really important that we communicate well. I mean, as you said at the beginning, I'm a scientist and a science communicator. And for me, science communication, I think, is incredibly important for a couple of reasons. Firstly, exoplanets is our generation. It was so recently, only the start of the 1990s, we didn't know of any other planets other than those in our solar system. And now you and I are sitting here in the middle of a pandemic discussing whether there could be life on other planets. I mean, actually discussing, not hypothetically, but what steps are people taking to find out if that's true? Yeah. That's a huge leap in a very short period of time. So I think you should always spend a lot of time on science communication because I don't think anyone should miss out on this journey. I think everyone should know exactly where we are, where we're going, and what the expectations are at this moment and what they'll be in 5 years' time. And I think that becomes even more important when you talk about the prospect of finding life. Because I worry that if people don't understand exactly what we might find, for a start, they might be disappointed or they might not know. That would be even worse. But also, as a human beings, we're a very religious nation. There's all sorts of different religions all over the world, and they're very, very important to people. How does finding life clip into philosophy and religion? I think that isn't trivial. And therefore, I think really clear communication about what we're likely to find, how like us we're expecting it to be, whether we're really going to make contact with it or not. I think all of that needs to be crystal clear to everyone so they can find their own place in the universe and not be scared or miss out.
And I think at the moment there is no consensus on how we should act. For example, some people are all for sending more and more information about humanity, like the Voyager disks. Others warn that we may be too reckless to do that because we expose ourselves. What is your position on this?
There isn't enough data. That's the problem. So when I talk about looking for biosignatures, I'm usually talking about non-intelligent life. So it wouldn't hurt us if we found it because it would be more like algae or equivalent, sort of micromolecular. And my theory for that is that as, intelligent life has to go through the non-intelligent stage first. So if you consider all the planets that could start life, I assume that many of them would reach intelligent life. Now, that's an assumption. We don't know. But if we assume that it's easier to reach stage 1 than it is to reach stage, I don't know what stage intelligent life would be, but presumably it's quite a long walk up that tree of life, then you would expect more planets to be at the bottom stage than at the top stage. So until we find even 1 or 2 more examples of even non-intelligent life, how can we assess the probability of finding intelligent life? And if we've got no idea what the probability of that is, then who knows whether there's any chance of the Voyager disks or anything else even reaching someone else's ears. So I feel the first stage is to look at the contents of these atmospheres and say, how common is any kind of life in the universe?
But you're saying, so if life as such is common, if there are traces of some maybe non-intelligent primitive life on many exoplanets, then there is quite a high probability that there is also intelligent life, if there is many examples.
The problem is there's certainly a higher chance than now. If we discovered that at least grade 1 life was very common, then there's certainly more opportunities for intelligent life to survive. But what's the probability of it really doing that? We come into something where we talk about bottlenecks. Like, where is the bottleneck? Yeah. Where is everyone? The Fermi paradox. Like, why haven't we already met all our alien neighbors?
Yeah.
And one possibility is life itself is rare. It just rarely occurs. Maybe all the planets in the habitable zone are like Mars. They don't have atmospheres, or they're like Venus with 2 thick atmospheres. And you just don't really get much life. The other option is you can start life, but it's really hard to continue it long enough for intelligent life to evolve. So that could be another bottleneck. And it's just very, very hard to speculate without seeing anything. Where are the bottlenecks? Do they exist? Are we just alone because we're first and actually it's pretty easy? Are we alone because the Earth is really rare? Or are we alone because everyone hates us? I mean, it's just very hard to know.
Well, wouldn't it be a bit arrogant for us as humans to assume that we are the only ones who have passed this filter, this stage where everyone is below us, only we have, due to evolution, reached this stage? Or would it be more modest to say that, well, probably if life exists and if evolutionary mechanisms work everywhere, which they probably should, then we may be not the only ones?
I think it's generally true that scientists like to believe they're typical, because you don't want to spend your life developing a set of laws that only apply to one place. The whole point in generating like a physical law or in chemistry and biology is you could apply it to everywhere. That's the whole idea. So it would be a little disappointing if we found that, okay, it works in this one case, but nowhere else. So in that sense, yes, I think we'd all like to feel that this could happen all over the galaxy and maybe one day we'll find someone else out there. But maybe also it's arrogant to say, well, unless there's other people like us out there, then space is wasted. Maybe, you could argue that the diversity of planets is also very exciting and actually quite a good use for that space, even without life forms that, cover it.
Yeah, for me, everything connected to space is very exciting, regardless of the fact that we do not know yet. It's so mind-blowing, I think, that there is such a huge variety of stuff in space. There are exoplanets, there are rogue planets, like planets that are completely on their own. And as far as I know, there are trillions of them, right?
There's maybe thought to be, because they're really hard to see, it's very hard to detect a rogue planet directly. But there is evidence based on sort of gravitational models that there's stuff out there we can't see, which could be rogue planets. And certainly when you build simulations of solar systems, you quite often end up ejecting a planet because the planets have big gravitational pulls, and as they start to pull on each other, sometimes they can just be knocked straight out the system. So actually a pretty successful model for forming our own solar system ends up with 5 gas giants and 1 is ejected. So it's certainly possible that this is the norm. And, for every solar system formed, there's 1 planet that just got voted off the island.
By the way, I'm interested. You must communicate a lot with your colleagues, fellow astrophysicists. Among them, what's the distribution on views on possibility of alien life? How many are optimistic?
I think we all want to be optimistic. But I think if you were to ask a little more quantitatively, and in fact, this debate has been had at conferences and we've got a panel of people and say, okay, you on the left, you're going to say life within our lifetime. And you on the right, you're going to say not a chance. And there's never a conclusion. The sides can really just go at each other with, a lot of really strong arguments in both directions. But, let's face it, we'd all find it exciting. So I think we're really all on the side that it would be amazing to discover an interesting signature that we couldn't quite explain through non-biological processes.
We've started discussing the topic of public perception of space and space-related topics. And you said that it's very important to communicate with the public, with the general public in the right way. I think, correct me if you disagree, but I think that currently we're not generally thinking very much about space. Maybe there are some events like new launches of spaceships that attract public attention, but still all those, for example, facts about exoplanets are really not known to the general public. So the question I want to ask is, do you agree that we should change something about it, that we should somehow tell people about space, educate them about it in a different way?
So I think there's a lot of interest from all sorts of people in space, which is great. I don't ever think you should need to become an astrophysicist to learn what's going on in astrophysics. I think, we should tell you. So I really feel the interest is there. What I find happens in my experience is that many newspaper or media publications, they go for a very fast, eye-catching headline, a sort of buzzy headline. And in that, they often lose accuracy. And it irritates me a lot because I'm just going to give an example. A classic headline in the last sort of 5 years is, "We've discovered the most Earth-like planet ever." And as I've just established, what that means is we know its radius is something like the Earth. But let's be clear here. Earth and Venus have the same radius. So you could equally say, "We've discovered the most Venus-like planet ever." And that suddenly sounds a lot less exciting, doesn't it? So I find that very irritating because we are going to start finding out something about these planets, and we're going to start finding maybe other Earths, other Venuses, other Marses, maybe something completely alien that we've never seen before. But if we tell everyone that we've already done it 10 years ago when we just meant radius, then people will get bored, or they won't believe us, or they just won't know it's coming up. And I don't know why you'd want to deprive someone of that journey. What we've discovered so far is amazing. We've discovered our solar system isn't alone. The universe is filled with planets, and the architecture of these systems and their sizes are completely different from our own solar system. It's wildly exciting. And the next step is going to be to find out what these planets are really like. And I get very annoyed with headlines that try and jump their gun to the end point and say, "Hey, we found another Earth." Because for a start, we might find something more interesting than Earth. And secondly, we haven't got there yet. And it's demeaning to tell people that we have. It's just lying to them. And they miss out on the incredible journey of where we are at the moment and where we're going to get to in the future. So if I could have my way and take over the world's media in a very, very dictatorial fashion, I would ban buzzy headlines. And instead I would try and tell people accurately where we are, because you don't need to hype it. It's really great. It's really exciting. And I would tell people clearly, where we're planning to be in 5 years' time and 10 years' time, so they can come along for the whole journey.
Do you think we, as humanity as a whole, are underinvesting in the space area, space exploration, space research?
I mean, obviously, I want to say yes, and that's a very biased viewpoint, because I obviously feel that all money should be in my field. But I do appreciate there are maybe some other fields that appreciate a bit of cash injection, especially at the moment. Maybe space isn't top priority. But one of the things I like about space is, while it is hard to fund because it's very expensive, it means that it's full of international collaborations, because it's very, very hard for any country to go to space alone. And so all the big missions, they're a combination of countries where we break down borders, we break down cultural barriers, and we say, actually, what we're looking for here isn't just the story of Japan or the UK or America or Russia. It's a story of Earth. We want to find out, are we alone? Are there other life forms out there? And actually, we all want to know the answer to that. So I love these international space missions where, different instruments and different components are contributed by different countries, all towards a common goal of finding out where we fit in the universe. So the expense is a downside. It does mean we can't all launch 100 Hubble Space Telescopes every day, but it also brings people together, and that's maybe a price worth paying.
Yeah, this is very inspiring for me as well. I hope that this cooperation will only grow deeper, and more people will get into fields after there will be some news about discovery of life on exoplanets. There will be a huge public enthusiasm, and this will all lead to the new renaissance of space, because I think we had one in the 60s, in the 1960s. Now we need a new one. You have definitely inspired me during this conversation, and I'm sure the viewers and listeners of this podcast are also very inspired right now. So thank you for that, Elizabeth. For those who are interested in digging deeper in this topic, I can recommend Elizabeth's book, The Planet Factory. I will give the link to Amazon page of that book in the description of this video on YouTube or podcast on podcasting platforms. If you liked the video or the podcast, click the like button and subscribe button, leave a comment in the comment section, or leave a review in the review section if you're listening to this podcast on the audio podcasting services. Thank you so much, Elizabeth. I hope we'll speak again in several years about some new discoveries that you make.
I hope so too.
I'm Greg Mustreader. See you next week.